In this Python script, various libraries are imported for conducting tasks related to data analysis, visualization, and modeling. Here's the breakdown of each imported library and its purpose. Firstly, importing OS enables Python to interact with the operating system for system-related operations. The Pandas library, imported as XGBoost, is crucial for data manipulation and analysis, offering powerful data structures like dataframes for structured data handling. The Matplotlib Pyplot library allows for creating a wide range of data visualizations such as plots and charts. Using Matplotlib, patches permits the drawing of shapes like rectangles and circles on plots. By importing Initialises, a high-level interface for creating appealing statistical graphics is made available. Building upon the functionality of Matplotlib, the warnings module aids in managing and suppressing warnings that may arise during code execution. For scientific computing, NumPy is a fundamental package providing extensive support for arrays and matrices. While from NumPy import array directly imports the array function into the script's workspace. The reload function from importlib eliminates the need to restart the Python kernel when modules require recloading. From Scikit-learn, naive Bayes comes the Gaussian naive Bayes classifier, a tool from the Scikit-learn machine learning library. Also, the classifier from XGBoost introduces the XGBoost classifier, featuring swift computation and high performance in gradient-boosted decision trees. To silence any generated warnings, filter warning signer sets up a filter to overlook them during execution. The linepult, or params figure, DP227 fine-tunes the DP setting within Matplotlib, affecting the resolution and quality of generated plots. Utilizing this code is vital for configuring the environment and bringing in critical libraries necessary for performing data analysis, visualization, and machine learning tasks effectively. Each library fulfills specific roles in facilitating data manipulation, visualization, and machine learning capabilities within Python. Importing these libraries establishes a solid foundation for carrying out data analysis and constructing machine learning models proficiently in a Python environment. In this code snippet, a variety of functions and classes are imported from different libraries to facilitate tasks related to statistical modeling, time series analysis, and machine learning evaluation. Let's delve into a brief rundown of each import statement. 1. Using an ALSTM, the statsmodels library is imported, offering tools for estimating and interpreting statistical models. 2. Specifically, the ARIMA model class is imported from the time series analysis module within statsmodels, commonly utilized for time series analysis and forecasting. 3. The SaramX model class from statsmodels, incorporating seasonal components and enhancing the capabilities of the ARIMA model, is imported for advanced time series analysis. 4. Functions for plotting partial autocorrelation function path and autocorrelation function fplots, crucial in determining ARIMA model order in time series analysis, or imported from statsmodels. 5. From the Scikit-learn library, evaluation metric functions such as mean squared error, confusion matrix, phone score, and accuracy score are imported. These metrics play a pivotal role in assessing performance in machine learning models. 6. To visualize autocorrelation in time series data, the autocorrelation plot function is imported directly from a Pandas data frame, aiding in identifying important time series characteristics. These imports are essential for working with time series data, constructing models like ARIMA and SaramX, evaluating model efficacy, and portraying time series features graphically. Each imported module offers a distinct set of functions and classes tailored to various facets of time series analysis and forecasting. The following script includes the importation of a range of modules and functions from TensorFlow and other libraries to aid in the construction and enhancement of neural network models. TensorFlow. Keras happens to be TensorFlow's rendition of the Keras API intended for the development of neural networks. Keras furnishes a user-friendly interface for creating and refining models. TensorFlow. Python Keras Optimizer 2. RMSprop incorporates the RMSprop optimizer from TensorFlow for optimization purposes during training. FunTools. Partial proofs handy for crafting partial functions within Python. TensorFlow. Keras Optimizers brings in a variety of optimization algorithms tailored for training neural network models. TensorFlow. Keras models. Along with TensorFlow, Keras layers present classes and functions for model construction and defining different layers. Bayesian optimization introduces the Bayesian optimization library, which serves the purpose of hyperparameter tuning in machine learning models. TensorFlow, Keras, plot model offers a function to generate a visually descriptive representation of the neural network model architecture. Through leveraging these imports, one would gain access to the essential tools and functions needed to effectively construct, train, and optimize neural network models within the TensorFlow framework. The code appears to be importing two modules or files labeled functions and plotting. The functions module likely contains tailor-made functions crafted by the developer to carry out specific tasks required for the program. These functions help streamline the code, enhance code reusability, and create a more structured main program. The plotting module probably houses functions or classes associated with data visualization or creating graph charts. This module may offer ready-to-use functions for generating various types of plots, simplifying the data visualization process for the developer without the need to start from scratch. By incorporating these modules, the main program gains access to the functions and classes defined in functions and plotting to efficiently execute the necessary operations and visualization tasks. It also aids in maintaining a tidy main program file and minimizing repetition by segregating distinct functionalities into individual modules. The code snippet establishes the seed value, 66, for the random number generator from the NumPy library. By defining a seed, it guarantees consistency in generating random numbers, producing the same sequence with each run. This practice holds significance in maintaining reproducibility in data analysis and scientific undertakings. Setting the seed allows others to replicate our outcomes effortlessly by adopting the identical seed value. The following script functions by scanning a directory named datastocks to compile a catalog of files and then constructs a stocks dictionary where it captures the contents of each C file in the form of a pandas data frame. Here's the breakdown of its operation 1. Initially, it retrieves a roster of files from the specific directory datastocks employing the os.lister function. 2. Subsequently, it proceeds to traverse each file within the acquired list. 3. With every file, the script verifies if it carries a SVI extension by segmenting the file name and examining the latter part of the split outcome. 4. Upon confirming the presence of a SVI extension, the file is loaded as a SVI file utilizing reds, and then the data frame is linked to the stocks dictionary with the file name minus the extension serving as the designated key. 5. It designates the date column as the primary index for the data frame. 6. The conversion of the index column to a datatime format is carried out using datatime. This script is indispensable for loading numerous SVI files from a designated directory, converting them into pandas data frames, and collectively processing or assessing the data encapsulated in these files. The functionality provided by this script streamlines the process of importing multiple files and preparing them for subsequent structured analysis or manipulation. The function called baseline model serves the purpose of establishing a simple baseline prediction model for a stock. This model operates by producing random predictions, either 0 or 1, based on the input stock data. The mechanism of this function is as follows to begin with. It accepts the stock data as an input parameter. Subsequently, it generates an array containing random binary values that match the length of the stock data. Following this, it assesses the accuracy of these arbitrary baseline predictions against the actual stock data using the ORESOR function. Lastly, it furnishes the accuracy metric of the baseline predictions. This script proves to be beneficial for establishing a fundamental reference point to gauge the effectiveness of more sophisticated prediction models. It aids in determining whether the advanced models offer substantial predictions beyond what random chance would provide. The following code snippet evaluates the effectiveness of a baseline model in predicting the returns of Tesla stocks based on the return column in the stocks data frames. The baseline model likely makes predictions using average returns or a straightforward rule derived from the data. To assess the accuracy of the baseline model, the code employs a predefined function called baseline model. The function's output, representing the accuracy, is then converted to a percentage by multiplying it by 100. Subsequently, the code displays the accuracy of the baseline model as a percentage with 1 decimal place. This metric acts as a benchmark for comparing the performance of more sophisticated models against the basic baseline model. It aids in determining if advanced models exhibit significantly superior performance compared to the simplistic approach, shedding light on the efficacy of the model development process. This code chunk works out forecasts using a basic model on a stock dataset, focusing specifically on the TSLA stock. It runs through 1,000 iterations and adds the forecasts to a list named dataset. Following the forecast generation, the code constructs a histogram to display the distribution of these forecasts. The histogram offers a glimpse into the baseline model's prediction accuracy for the stock returns. The dashed black line on the histogram depicts the average of the predictions. This graphical representation aids in grasping both the range and central tendency of the predictions made by the baseline model. This piece of code plays a crucial role in assessing the baseline model's performance and obtaining insights into its efficacy in predicting stock returns. By visually depicting the distribution of predictions, we can evaluate the precision and variability of the model. This snippet is likely part of a project handling data or creating visuals concerning TSLA stock information. The initial line outputs the count of records in the historical TSLA stock data. It achieves this by fetching the rows count from the TSLA dataset stored in stock TSLA. Following that, the next line extracts the return column from the TSLA stock records and exhibits the initial few rows. This action involves utilizing double square brackets to isolate the dataset and calling the head method to exhibit only the initial records. Employing this snippet aids in swiftly summarizing the data, including the entry count and data configuration, for subsequent analysis or visualization purposes. The purpose of this code snippet is to resize the figure for presenting a plot and then create an autocorrelation plot for the daily returns of TSLA stock. Let's delve into what each part of the code accomplishes. 1. Setting the default figure size to 16:3 inches using PULT, or params figure. Fig size. 2. Drawing an autocorrelation plot F for TSLA stock's daily return data with lags ranging up to 300 by executing plot F stock SLA. Return clagscrange 300. 3. Exhibiting the plot on the screen with the PULT show function. An autocorrelation plot serves to visualize the autocorrelation within a time series dataset. In this instance, it aids in identifying potential autocorrelation within TSLA stock's daily returns across various lags up to 300 days here. This plot analysis allows us to discern trends and behaviors in stock returns, thus facilitating predictive modeling and forecasting efforts effectively. This excerpt is extracted from a program that aims to forecast stock returns by exploring various ARIMA orders. Let me break it down for you. Initially, a list of orders is defined to encapsulate diverse combinations of the ARIMA model parameters P, D, Q. Subsequently, each order is traversed one by one to fit an ARIMA model with that particular order. Within the loop, the program utilizes the ARIMA function from a library not disclosed to shape a model and trains it on the available data via model fit. Following that, the trained model is leveraged to predict the upcoming return value, which is then appended to a collection of forecast order predictions. The accuracy of these predictions is then evaluated using the ARISOR function on binary representations of the actual and forecasted values. Throughout the process, the program showcases the outcomes, encompassing the order, accuracy rate, and any encountered discrepancies. This section of code holds paramount importance in assessing and contrasting the efficacy of different ARIMA orders in predicting stock returns. By experimenting with diverse orders and gauging their precision, the program can pinpoint the optimal model order tailored for this specific prediction assignment. This iterative method plays a pivotal role in refining the ARIMA model's hyperparameters to enhance forecast precision. Utilizing the matplotlib library in Python, this piece of code generates an intricate visualization. Initially, a figure is crafted, specifying its size with PULT. Figure fixes a 16. 4. Next, two distinct line plots, test and predictions, are incorporated into the figure utilizing PULT. Plot each assigns specific colors. To illuminate these lines, a legend is included, along with tailored titles, axis, and y-axis labels, further enhancing the visualization. An annotation is included to pinpoint a particular section on the graph. Subsequently, a subplot is introduced through fig cat subplotone 1.1, showcasing a rectangular patch with patches. Rectangle, highlighting a specific region within the plot, expanding on the visualization. Another subplot is fashioned using PULT, axis 25.1.2. 5. To present a magnified view of the initial 30 data points. The test and predictions lines for the first 30 data points are delineated, concealing the axis labels via pult, tick parenthesis above, label bottom faus, label left faus. A distinct title is designated for this compact subplot. This code serves to visually juxtapose the test data against predictions derived from an ARIMA model, accentuating precise areas of interest within the plot. By offering insights into the model's predictions, it enables users to assess its performance visually. The following script creates a histogram to illustrate the comparison between real and forecasted values derived from a time series examination 1. It initializes a plot with dimensions of 16.5 inches. 2. The plot showcases a histogram of the actual return data of a specific stock TSLA within the range of indices 1900 to 2300. Employing 20 bins represented by bars colored in 4 3. Overlaid on this is a second histogram representing the predicted return values from the ARIMA model, featured in T4 color with 70 transparency. 4. A vertical dashed line is included at K0 for points of reference. 5. The plot is labeled ARIMA true versus predicted values distribution. 6. Additionally, a legend is incorporated on the plot to distinguish between the true and predicted values. This code proves valuable for visually examining and contrasting the distribution of actual and predicted values derived from an ARIMA model. Through the use of histograms, it becomes easier to grasp the value spread and make visual comparisons. The X line serves as a crucial point of reference at 0, indicating how data is dispersed around that particular mark. The legend simplifies the differentiation between actual and forecasted values within the visualization. The snippet of code seems to be focused on assessing the performance metrics of a binary classification model on a test dataset. Let's delve into what it accomplishes to start. It translates the stock returns for TSLA into binary form within a specified range and saves them in the test binary variable. Following that, it generates binary representations of the predictions from the help predictions data and stores them in the train binary variable. Next, the script proceeds to compute the confusion matrix for both the test and train binary predictions. This matrix furnishes valuable insights into the model's efficiency by revealing true positives, true negatives, false positives, and false negatives. The values from the confusion matrix are then extracted into individual variables T and tip. The accuracy score is determined by comparing the binary predictions from the test and train sets and is kept in the accuracy variable. Lastly, it showcases the combined sum of true positives and true negatives, the cumulative sum of false positives and false negatives, along with the accuracy of the model expressed in percentage form. This code plays a pivotal role in evaluating the performance of a binary classification model on a dataset. By furnishing metrics like accuracy, true positives, true negatives, false positives, and false negatives, it aids in gauging the model's predictive prowess. These metrics are instrumental in gauging the model's accuracy and serve as a compass for refining the model further or benchmarking it against other models. The following snippet of code is designed to import a CT file called TSLA headlines into a pandas data frame. Each row in the data frame corresponds to a headline linked to TSLA. With the indexal parameter, we specify that the data frame should use the date column from the CT file as its index. This approach streamlines the organization of data and simplifies accessing information based on dates. Employing this code enables us to transform the headline data into a structured format, facilitating seamless manipulation and analysis using the robust functionalities of the Pandas library in Python. Leveraging Pandas dataframes empowers us to execute diverse tasks related to data manipulation, analysis, and visualization in a highly effective manner. Combining data frames is a common practice in data analysis. In this scenario, the aim is to merge two data frames, one containing TSLA stock data labeled as TSLA, and the other comprised of average sentiment scores from TSLA-related headlines grouped by date. This is typically achieved through the use of the join function, which horizontally merges the data frames based on a shared column, most likely the date column. This method of merging data frames is advantageous for integrating and examining disparate datasets holding interconnected information. By consolidating these datasets, analysts can conduct comprehensive evaluations that incorporate both Tesla's stock performance and the sentiment reflected in news headlines concerning Tesla on corresponding dates. This approach enables the extraction of valuable insights into the potential impact of news sentiment on stock price fluctuations. This snippet of code is designed to replace any non-values in the data frame called Tesla with zeros. By setting imply true, the adjustments are applied directly to the existing data frame. Avoiding the creation of a new one, substituting missing values with zeros proves beneficial in situations where it is appropriate to interpret absent data as zero, particularly in mathematical computations or data assessments. Moreover, assigning zero could hold significance within the dataset. This approach aids in managing absent data, safeguarding against inaccuracies in computations or evaluations, and maintaining the dataset's coherence and entirety. Utilizing Matplotlib, this code excerpt generates a line plot to depict Tesla's news sentiment and daily return relationship. It customizes the visual style by setting it to Seaborn Widegrid and specifies a figure size of 16:6 units with pult. Figure fixes a 16:6. The plot showcases two datasets within the timeframe from 2019 content to 2019-951. A blue line plot representing sentiment data, shifted by 1 day to display previous day's values 3,588. 2. A pink line plot illustrating return data 497. Following data plotting, the script includes a legend with customizable features like a framed fancy box appearance, adjustable frame transparency, and specific location settings. To conclude, a title Tesla News Sentiment and Daily Return with a font size of 15 is assigned to the plot. The purpose of this code is to visually analyze the potential correlation or recurring patterns between Tesla's news sentiment and daily return during the outlined period. The plot acts as a valuable tool for analysts, traders, or researchers to interpret the data swiftly, extracting meaningful insights from the displayed information. The following script generates a correlation matrix comparing two specific columns within a data frame. These columns contain sentiment and return data related to Tesla's stock during a particular period, ranging from January 10, 2019 to September 5, 2019. To break it down, 1. It initiates a data frame through the Pandas library, featuring columns labeled sentiment and return. 2. The sentiment column is populated with sentiment values concerning Tesla's stock within the specified date range. By utilizing the shift-tone function, the sentiment values are shifted by one position to synchronize the data for correlation analysis. 3. The return column is then populated with the corresponding return values of Tesla's stock over the defined time frame. 4. Afterward, the script employs the core function on this data frame to compute the correlation between the sentiment and return columns. This code serves the purpose of examining the connection or correlation existing between sentiment values and stock returns associated with Tesla during a specific span. Grasping this correlation aids in making well-informed decisions or forecasts regarding stock performance based on the sentiments of investors or the general populace. Utilizing a function called scale from an external module or library labeled functions, the code aims to rescale the values within the TSLA column of a data frame named stocks. Scaling serves as a fundamental preprocessing technique in data analysis and machine learning, facilitating the adjustment of data to conform to a specified range, often spanning from 0 to 1. This practice is instrumental in optimizing the efficacy and convergence of particular machine learning algorithms, particularly those sensitive to feature input scales. In this scenario, it is probable that the scale function is normalizing the values in the TSLA column of the stock's data frame to a range between 0 and 1. This standardized data can subsequently be leveraged in subsequent analytical pursuits or modeling endeavors. The following code snippet has been designed to preprocess data for a machine learning model, specifically tailored for time series forecasting. Let's break down each line. 1. Setting X sales like 1 in this line. A featured dataset named X is established by excluding the last row from the sales dataset. Typically, each row in X represents a distinct time point such as a day or an hour containing scaled features relevant to that specific moment in time. 2. Defining Y stocks return. Shift 1. This line constructs a target dataset denoted as Y for the machine learning model. The return column from the TSLA stock data is selected, and the values are shifted by one time step using Shift 1 before excluding the final row. This adjustment ensures that the target values are aligned with the corresponding feature values in X. The primary objective is to forecast the future return based on the present features. In the realm of time series forecasting, it is vital to synchronize the features and target appropriately to enable the model to learn and predict forthcoming values based on historical data patterns. By structuring X and Y in this manner, the model can effectively grasp the underlying data patterns and generate accurate predictions. In this code snippet, XGBoost classifier model is being trained with data X and target values Y. With the first 1500 samples excluded, here's a breakdown of what the code accomplishes. 1. Initializing a new XGBoost classifier model by creating an instance of classifier. 2. Training the XGBoost classifier model using XGB. Fit 1500, a 1500. This line invokes the fit method on the XGBoost classifier to facilitate model training. X represents the input features data, and Y stands for the target labels. The code excludes the initial 1500 samples from the training data by slicing X and Y with 1500. Such an approach proves beneficial when segregating data for training, testing, or validation purposes. This code snippet serves as a valuable tool in machine learning endeavors, especially when aiming to train a model with a selected portion of the dataset. Like dividing it into training and testing subsets, training the model with a fraction of the data enables evaluation of its performance on fresh data and helps to deter overfitting. The provided code snippet offers a visual representation of the significance of various variables within a dataset by leveraging XGBoost. Let's delve into the functionalities of this code. 1. Establishes a data frame named important features comprising 2 columns, feature housing the feature names from the X DataFrame X. Columns and importance containing feature importance stored from the XGBoost model HEGB. Features importance. 2. Organizes the important features data frame in ascending order based on the values in the importance column. 3. Generates a bar plot illustrating the importance of each individual feature, showcasing features along the y-axis and their respective importance along the x-axis. 4. Adopts the Seaborn-White grid style for an enhanced visual appeal of the plot. 5. Presents the bar plot with each feature's importance denoted by a shade of blue for AFB. 6. Titles the plot as XGBoost feature importance TSLA. Designates importance for the x-axis label. Recognizing feature importance is pivotal for elucidating the model's forecasts and pinpointing the most influential features in forecasting the target variable. This visual aid facilitates the recognition of critical features and comprehension of their influence on the model's outcomes. Moreover, it assists in feature curation and refinement to elevate the model's efficacy and interpretability. This code excerpt readies the data for a time series prediction model using a recurrent neural network RNN or a similar sequential model. Let's dissect the code step by step. 1. Setting the steps. 21 establishes the number of time steps representing days to be included in each input sample. 2. By invoking TSLA functions, TSLA SLA, SLA 1, the TSLA stock data is standardized to a predefined range, typically spanning from 0 to 1. This normalization aids in hastening the model's learning process and prevents any single feature from overpowering others. 3. Following that, the split sequences function is invoked with the subsequent parameters TSLA. TONUMP1 represents the input sequences for the model, where each sample comprises a sequence of past stock prices excluding the last data point for forecasting purposes. Stock SLA, return, Shift 1. TONUMP1 denotes the target values for the model, which reflect the returns of the TSLA stock for the subsequent time step. NN step signifies the number of time steps to be incorporated in each input sequence. Split true signals the intention to divide the data into training and testing datasets. Ratios row 8 dictates the split ratio between training and testing datasets, 80 for training and 20 for testing. Essentially, this code segment prepares historical stock price data pertaining to the TSLA stock for ingestion into a machine learning model designed for time series prediction. Through data normalization and segmentation into input sequences and target values, we are structuring the data suitably for the model to discern from. This code snippet is pivotal for efficiently preprocessing the data and ensuring that the model can identify patterns and furnish precise forecasts based on historical stock price data. Below is a human-generated code snippet showcasing the creation of a neural network model tailored for sequence prediction purposes using the Keras library in conjunction with a TensorFlow backend to kick things off. The Keras backend clear session line acts as the key player here, wiping the slate clean by resetting the Keras session and thus ensuring a fresh start for each new model. By doing so, the model avoids any baggage from prior models, such as weights or biases, thereby maintaining a tidy memory space. Next up, we set the scene by defining the number of time steps referred to as n-steps and the number of features designated as n-features present in the input data. Moving along, we construct a sequential model, a simple yet effective approach where layers are neatly stacked one after the other in a linear fashion. Here's where the magic unfolds. Some long short-term memory layers step into the limelight. Known for handling long-term dependencies like a champ, the first Tulsum layer boasts 100 units and dishes out sequences for the subsequent layer to feast on, while the second one shines with 50 units. Not stopping there, we spice things up with a sprinkle of two dense fully connected layers, sporting 10 and 1 units, respectively. The final dense layer with a single unit takes center stage, primarily tailored for regression concerns, housing a sole numerical target variable, promising a singular prediction output. After this modeling masterpiece, it's time to compile the model. Cue the ATOM optimizer. Mean squared error may as the loss function, alongside mean absolute error may serving as a watchful eye during training. The ATOM optimizer's charm lies in its knack for adjusting the learning rate dynamically, fine-tuning the training process for optimal convergence. In a nutshell, this code piece meticulously crafts a neural network blueprint geared towards tackling sequence prediction challenges head-on. Equipped with the prowess of the Keras library and the adeptness of a clean session, ensuring a streamlined and efficient deep learning journey with a knack for memory optimization. In the realm of machine learning, the model summary function plays a crucial role in presenting a brief yet insightful overview of a neural network model's structure and parameters. This snapshot encapsulates essential details about each layer within the model, encompassing specifics like the layer type, output shape, as well as the count of parameters, both trainable and non-trainable, per layer. Utilizing model summary permits a swift examination of your model's architecture, aiding tremendously in tasks like debugging, comprehending the data flow across layers, and verifying the model's intended configuration. This feature proves particularly invaluable for intricate neural networks with numerous layers, offering a convenient glimpse of the entire model's composition. In this code snippet, a machine learning model is being trained over 100 epochs using the provided training data train. The training advancement is monitored through tracking the loss values. Furthermore, it leverages the validation data test. You test to assess the model's performance as it progresses by evaluating the validation loss. Following the training phase, Matplotlib is utilized to create a plot that visually represents the model's training journey. The plot exhibits the evolution of both the training and validation losses across the epochs, enabling us to scrutinize the model's performance and ascertain whether it exhibits signs of overfitting or underfitting. Employing this code snippet is vital for overseeing the machine learning model's training process, fine-tuning hyperparameters, and verifying that the model is effectively learning from the data without overfitting. Observing the training advancement aids in making well-informed decisions aimed at enhancing the model's overall performance. This segment of code appears to utilize a custom function called functions evaluation to gauge the effectiveness of a machine learning model on a test dataset. The function's parameters and anticipated functionalities are described below. Test and test represent the features and labels of the test dataset. Model denotes the machine learning model under evaluation. Random false. This parameter determines whether the function should utilize random predictions for comparison. When set to true, the function may generate random predictions for evaluation purposes. If set to false, the model's predictions will be used instead. NPREDS 50 specifies the quantity of predictions to generate if random predictions are activated. ShowGraphTrue governs the potential display of a graph by the evaluation function. If set to true, the function may exhibit a graph to visually represent the evaluation outcomes. The function presumably calculates assessment metrics such as accuracy, precision, recall, phone score, among others, to evaluate the model's performance. These metrics are derived by contrasting the model's predictions or random predictions with the actual values. Leveraging this bespoke evaluation function proves advantageous as it furnishes a comprehensive set of evaluation metrics and potential visual aids. Streamlining the interpretation of the model's efficacy, it establishes a uniform and reliable method for gauging the model's performance across diverse datasets and models. Below is a typical process illustrating the creation of a deep learning model using Keras with a TensorFlow backend. Here's an outline of what it accomplishes to kick things off. The snippet leverages Keras backend clear session to reset the TensorFlow graph within the Keras session. This step proves handy when initiating a fresh model or conducting various experiments sans the baggage from earlier runs, ultimately freeing up memory and related resources associated with prior models. Next in the sequence, the snippet proceeds to establish the structure of the neural network model. It defines the input shape by gauging the dimensions of the training data trained to pinpoint the number of time steps in features. Sets up a one convolutional layer followed by a subsequent max-pooling layer. Flattens the convolutional layer's output to seamlessly channel it into densely connected layers. Incorporates two dense layers fully connected, featuring ReLU activation functions for the hidden layers and a linear activation function for the output layer. Wraps up by compiling the model with an atom optimizer and a mean-squared error maze loss function. By executing the above steps, the script shapes a convolutional neural network CNN architecture tailored for applications like time series forecasting or processing sequence data. The inclusion of clear session proves crucial in staving off conflicts that may arise when managing multiple models within a single script or notebook. The model summary function is a handy tool found in various deep learning frameworks like TensorFlow or Keras. It allows users to get a quick overview of their neural network model's architecture. This summary includes details about the layers present in the model, the shape of the output from each layer, as well as the count of parameters both trainable and non-trainable, and the overall parameter tally of the model. This function comes in handy for troubleshooting and confirming the correctness of the model structure adhering to our design specifications. By examining the summary, we can promptly verify if the model matches our intended architecture, encompassing details such as layer count, layer types, and data flow amidst layers. Getting these aspects right is vital to ensure that the model is correctly set up before moving on to training it with real-world data. The utility of model summary shines through especially with large or intricate models, offering a concise glimpse into the model's configuration. This makes it simpler to spot and address any potential issues that may crop up along the way. This snippet of code serves the purpose of training a neural network model by utilizing the provided training data, XTrain and UTrain, through 25 training epochs. Throughout the training process, it records the metrics of training and validation loss without displaying the progress output by setting verbose 0. The validation data is essential for assessing the model's performance on new, unseen data. Post-training, the script generates a graphical representation depicting the progression of training and validation loss values against the number of epochs. Courtesy of Matplotlib, this graphical aid aids in gauging the model's learning trajectory during training, enabling identification of any potential coverfitting or underfitting issues. To achieve this visualization, the plot function is employed to plot the training loss and validation loss extracted from model history, loss, and model history of all class. Correspondingly, in essence, this code excerpt equips you with the capability to train a neural network model, visualize the training dynamics, and assess the model's performance concerning the validation data. It facilitates the monitoring of the model's learning evolution, enabling informed decisions on potential enhancements to the model if required. It looks like this code is a segment of a broader program dedicated to assessing the performance of a machine learning model through a specific evaluation function. In this snippet, the functions evaluation is invoked with various parameters. Cotest and utest are the test input features and respective target values. The model stands for the specific machine learning model under assessment. Setting random false specifies a non-randomized evaluation process. By setting inputs 50s, the function will make 50 predictions for evaluation. Showgraph true signals that a graphical representation of the evaluation findings will be presented. The function appears to calculate metrics for appraising the model's predictions and performance on the test dataset. It presumably produces three outputs: pred, utrue, and upred, likely corresponding to predictions, actual targets, and predicted targets, respectively. This piece of code plays a crucial role in objectively evaluating the model's performance, pinpointing issues like overfitting or underfitting, and determining the necessity for further model fine-tuning. In essence, this evaluation aids in gauging how effectively the model generalizes to fresh, unseen data and whether it's primed for deployment. The following snippet merges various data frames into one cohesive data frame. In pandas, the concat function is employed for this task, concatenating data frames along a specified axis. By default, this function stacks rows on top of each other, indicating concatenation along axis 0. In this scenario, the parameter ignores index true is utilized to reset the resulting data frame's index. When concatenating multiple data frames, the new data frame might retain the original index values. To address this, setting ignores index true guarantees a fresh sequential integer index for the resulting data frame, commencing from 0. This code facilitates the amalgamation of multiple data frames into a singular data frame, particularly valuable when consolidating data from diverse sources or processes. Such integration proves beneficial in tasks involving data manipulation, analysis, and visualization, providing the convenience of working with a unified dataset over managing multiple fragmented datasets. This snippet of code forms part of the process to ready financial stock data for a machine learning model. Let's dive into what the code accomplishes to start. Cell functions. Celil stocks, Celil 1 scales the cell stocks dataset using the scale function from the functions module, adjusting values to a range between 0 and 1. Next, setting this steps 21 establishes the number of previous steps the model will consider as input features, essentially looking back 21 days in the data for making predictions. Proceeding with Histogram, Yetrain, Custist, Neatest functions, splitskins. Saledol, TONUMP1 serves as the model's input data X, representing scaled historical stock data excluding the latest point, which will be used as the target for prediction. Call stocks return, shift 1. TONUMP1 represents the target data Y for the model, showing returns of the following day shifted back by 1 day. NSteps indicates the number of steps utilized for each sequence in the training set. Split true prompts the function to divide the data into training and testing sets. Ratio 0.8 specifies that 80 of the data will train the model, allocating 20 for testing. Essentially, this code readies historical stock data for the machine learning model by scaling and separating it into training features train and label targets utrain, alongside performing similar actions for the test dataset utest. This preliminary step is vital to ensure the model can effectively learn from the data and issue accurate predictions. The script you see here constructs a convolutional neural network CNN utilizing the Keras library. Outlined below are the functions of the script. 1. To begin, Keras backend clear session is implemented to wipe the current Keras session and reset the TensorFlow graph. This step is crucial to prevent any discrepancies or memory overflow before initializing a new model. 2. The subsequent commands establish the input data's structure and formulate a sequential model. The steps and NIN features are computed based on the shape of the input data train. The model's composition is as follows: an initial 1 convolutional layer onVund containing 500 filters and a kernel size of 10. Applying the ReLU activation function, a max pooling layer max pooling end with a pool size of 10. A flattened layer transforms the 2 convolutional layer output into a 1 vector. Following are 3 dense layers dense with 500, 100, and 1 neurons respectively, all utilizing ReLU activation except the final layer that adopts a sigmoid activation. The model is then compiled using the atom optimizer and mean squared error mace loss function. Deciphering the script is crafting a CNN model tailored for classification or regression endeavors. It assumes the model is intended for 1 data, where NSteps possibly denotes the time steps or sequence length, while NIN features represent the features at each time step. The convolutional layer aids in recognizing spatial hierarchies within the input. Max pooling aids in dimensionality reduction of the spatial data. The later dense layers introduce nonlinear alterations to the acquired features. The primary objective of the model is to forecast a single output value, as inferred from the final dense layer with one neuron and a sigmoid activation. The optimization process utilizes the ATOM optimizer while employing MACE as the training loss function. Utilization: it is vital to clear the Keras session before commencing a new model to ensure a seamless progression and avoid any clashes or memory overflow among models. The construction of a CNN model in Keras involves orderly stacking of layers to devise a deep learning framework optimized for processing one data like time series or signal data. Within the realm of neural network training lies this code snippet tailored for honing a model using training data train. I train and scrutinizing it against validation data test. I test. Let's delve into what the code accomplishes and why it carries significance. 1. The line model. Fit train, a train, a post 25, verbose 0, validation data test, a test. Use multiprocessing true undertakes the actual training of the neural network model. It delineates 25 training epochs, suppresses training output by setting verbose 0. Evaluates model performance using validation data, and boosts training speed through multiprocessing where feasible. 2. Initializing a matplotlib figure with a size specification of 16 by 4 prompts the line plot. Figure fixes a 16. 4. To launch the plotting of training and validation loss curves. 3. By executing plot model, history, historical loss label class in conjunction with plot model, history class, label loss. The loss values from training and validation phases are graphed throughout the training process. These loss metrics are stored within the model. History object post model fitting. 4. The inclusion of plot legend lobon in the code imbues the plotted graph with a legend, facilitating a clear differentiation between training and validation loss trends. 5. A call to plot show concludes this sequence by rendering the loss curve plot visible. Surveying the loss curves amid model training plays a pivotal role in monitoring performance and flagging potential concerns like overfitting or underfitting. It empowers decision-making by offering insights to refine the model architecture, hyperparameters, or dataset, ultimately fostering a more effective neural network model. This snippet of code appears to be aimed at assessing the effectiveness of a machine learning model. Let me break down what the code accomplishes to start off. It invokes a personalized function called evaluation from a module or file dubbed functions. Next, it feeds specific parameters to the function test the dataset employed to scrutinize the model's performance. Test the actual labels corresponding to the test data. Model the trained machine learning model up for evaluation. Random truth. This argument could imply that the function is set to produce predictions randomly. In Predscone 100, this parameter dictates the quantity of forecasts utilized for assessment. Show graph true. This configuration suggests that the function might exhibit a graphical representation following the evaluation process. The objective of implementing this code is to gauge how effectively the machine learning model functions on new, unseen data test by juxtaposing its predictions UPRT against the genuine labels true and potentially visualizing the evaluation findings via a graph. Such an evaluation endeavor is pivotal for comprehending the model's precision, recall, accuracy, or any other pertinent metrics, enabling informed decisions regarding the model's performance and potential enhancements. The provided code outlines a function named greetModel responsible for forming and training a convolutional neural network CNN model through the employment of the Keras library in conjunction with the TensorFlow backend. The function's workflow can be outlined as follows. 1. A pivotal step involves clearing the Keras session to guarantee the inception of a fresh model devoid of any residual influence from preceding models. 2. The function harmonizes input parameters such as done, do, filters, kernel, and pool into integers for seamless processing. 3. By analyzing the shape of the training data train, the function discerns the time steps and features prevalent in the input data. 4. Subsequently, the function initiates the creation of a sequential model, entailing a linear stack of layers. 5. Incorporation of a one convolutional layer equipped with the specified number of filters. Kernel size. An activation function of ReLU ensues. 6. A one max pooling layer with the designated pool size is introduced. 7. The output stemming from the convolutional and max pooling layers is flattened. 8. Two fully connected dense layers, each housing done and D2 units along with ReLU activation functions. are appended. 9. The conclusive step involves integrating the final output layer containing a singular unit customized for regression tasks. 10. The model is compiled utilizing the ATOM optimizer while adopting mean-squared error MACE as the designated loss function. 11. Post-compilation. The model undergoes training on the training data Histogram and Jupyter, entailing 4 epochs. 12. Subsequently, model performance evaluation is conducted on the test data test and test. 13. Ultimately, the function calls the mean-squared error MACE resultant from the evaluation outcomes. This code is indispensable for the creation, compilation, training, and evaluation of a convolutional neural network model calibrated for regression tasks. Evidently, the code serves as an automation tool facilitating the model creation and training process, thereby streamlining workflow and furnishing a standardized approach for exploring various model architectures and hyperparameters. This code snippet exemplifies the utilization of Bayesian optimization, an approach employed to identify the optimal hyperparameter configuration for a machine learning model. It is highly probable that this specific situation involves fine-tuning the hyperparameters of a neural network model. Let's break down what the code accomplishes. 1. It establishes a dictionary named bounds that delineates the exploration space for the hyperparameters. The values within this dictionary define the intervals within which the optimizer will seek the most favorable values for each hyperparameter. 2. The code instigates a Bayesian optimization object labeled optimizer through the instantiation of the Bayesian optimization class. Within this initialization, the f parameter designates the objective function that the optimizer will endeavor to enhance. In this context, it refers to the create model function. The bounds parameter delineates the previously defined exploration space. Furthermore, random state is configured to manage randomization and ensure reproducibility, while verbose is adjusted to 2 to exhibit intermediate output during the optimization process. 3. The code invokes the maximize method on the optimizer object, incorporating the parameters init points 5 and iter 5. These parameters specify the quantity of initial random points to explore and the total number of optimization steps to execute. 4. Ultimately, the code displays the hyperparameters optimizer max that yielded the highest objective function value upon the completion of the optimization process. In essence, this code snippet leverages Bayesian optimization to effectively explore the optimal hyperparameters for a machine learning model, with the aim of boosting the model's performance without resorting to exhaustive manual tweaking. In this code snippet, data is being prepped to train a machine learning model that predicts future returns on Tesla stocks. Here's a breakdown of what the code accomplishes. Firstly, it initializes the variable missteps to 21, which signifies the number of time steps considered for the model's input data. Next, the historical Tesla stock data is normalized between 0 and 1 using a scaling function called scale. After that, split sequences function is applied to craft sequences of inputs and outputs for the model. This function takes the scaled Tesla stock data and adjusted returns as arguments. The historical Tesla stock data is denoted as HTrain, and the corresponding future returns as UTrain. Similarly, cutest and UTest are prepared for testing the model's efficacy. The data splitting is set at an 80 training and 20 testing ratio, steered by the ratio 0.8 parameter. This code is pivotal to structure the data suitably for training the machine learning model, ensuring proper input-output sequence lengths and precise train test divisions for accurate forecasting of Tesla stock returns down the line. Bayesian optimization is a nifty technique employed to pinpoint the overall best result of a function without exhaustively checking all potential points. The approach involves consistently constructing a substitute function based on observed values and their associated uncertainties. Reflecting the Bayesian belief regarding the authentic objective function, this surrogate function is then utilized to determine the subsequent point for assessment by balancing between exploration sampling in areas with uncertain function behavior and exploitation sampling in areas where the function is likely to be at its best. Within the realm of machine learning, Bayesian optimization commonly comes into play for fine-tuning hyperparameters of machine learning algorithms. By treating hyperparameter adjustment as a mystery optimization conundrum, Bayesian optimization becomes adept at efficiently exploring hyperparameters that enhance the model's performance on a validation set. This streamlines the process of identifying the optimal hyperparameters for a specific model. cutting down time and energy compared to grid or random search methods. In this script, a neural network model is crafted utilizing the Keras library, specialized for handling time series data. Each segment of the code serves a distinct purpose. 1. Establishing variables n steps train, shapeicon and nin features train. Shape2 determines the quantity of time steps and features in the input data, critical for shaping the model's input configuration later on. 2. Employing Keras backend. Clear session eliminates any potential interference from prior models or layers within the Keras backend, ensuring a clean slate for the current model construction. 3. Initiating a sequential model using model sequential lays the foundation for a layered approach, allowing for sequential addition of layers. 4. Incorporating model. Add Hanvan filters 9. Kernel size of 5. Activation relu. Input ship and steps. N features introduces a quant convolutional layer to the model, filtering out 9 features with a kernel size of 5 and employing the relu activation function. This layer plays a crucial role in extracting features and time series data. 5. Adding model. Add max pooling and pool size of 9 inserts a quant max pooling layer into the model with a pool size of 9, effectively reducing the dimensionality of data derived from the convolutional layer. 6. Introducing model. Add flatten integrates a flattening layer into the model, converting the 2D output from prior layers into a quant tensor for seamless integration into the dense layers. 7. Incorporating model. Add denset 250. Activation relu incorporates a fully connected dense layer featuring 250 units and relu activation for intricate nonlinear feature mapping. 8. Capending model. Add densiton. Activation relu introduces an additional dense layer comprising 10 units with relu activation for further feature mapping. 9. Adding model. Add densicon finalizes the network with an output layer containing a single unit tailored for regression tasks. 10. Concluding with model. Compile optimizer kadam. Clauses, metricisms. The model is compiled with specifications including the atom optimizer, mean squared error mace as the regression loss function, and mace utilized as the evaluation metric throughout training. This script serves a pivotal role in crafting a neural network model optimized for time series data, incorporating convolutional and dense layers proficient in feature extraction and regression tasks. By customizing the architecture and parameters, the model aims to discern intricate patterns within time series data to facilitate accurate predictions. This excerpt delves into the process of training a neural network model by employing the fit function, showcasing training and validation losses through matplotlib, and appraising the model's efficacy on a test set. The initial model fit operation involves training the neural network model referred to as model by feeding it the training data train along with labels utrain. It runs for 100 epochs with the parameter verbosa 0 to mute the training output. Furthermore, it incorporates validation data test and utest for training purposes, enabling use of multiprocessing. True aims to accelerate data processing by tapping into multiple PU cores. Following that, the PULT, figure and PULT, plot functions jump into graph the training and validation loss values retrieved from model. History. This graphical representation offers a glimpse into the decline of loss throughout the training epochs, shedding light on the model's learning trajectory and the possibility of overfitting. To cap it off, the evaluation functions. Evaluation is activated to gauge the model's proficiency on the test data. It scrutinizes and contrasts the model's predictions spread against the actual labels truth. Incorporating a smidgen of randomness random truth in the assessment procedure, it churns out multiple forecasts per sample and predsca 100. The show graph true parameter hints at a visual display, likely featuring accuracy metrics or prediction illustrations for further analysis. To summarize, these code snippets play a pivotal role in the lifecycle of deep learning models. Pivotal for their training, monitoring, and evaluation, they furnish crucial insights into the model's performance, training evolution, and avenues for enhancement. The following Python script generates a graphical representation showing stock returns for a particular stock dataset SLA over various timeframes. It leverages the matplotlib library to craft the plot with the following characteristics, setting the dimensions of the plot to 16.5 inches through PULT. Figure fixes a 16.5, choosing a white grid background style with PULT style. Uses eborn white grid, using PULT plot to graph the stock returns data, distinguishing two data segments by employing different line styles and colors. Incorporating a legend onto the plot to specify the nature of the displayed data using Pult. Legend, titling the plot as patterns and testing set with a font size of 15 via Pult. Title, labeling the y-axis of the plot as return with Pult. ilabo return, displaying the plot with all the specified features by calling Pult. Show, this script proves handy for visualizing stock return information, contrasting various segments or trends within the dataset, and pinpointing any connections or irregularities. It aids in visually comprehending the trends and patterns inherent in the stock return data, offering insights that can be beneficial for investment decisions or evaluating stock performance. The task at hand involves the utilization of code to analyze binary time series data through pattern matching and prediction methods. Here's a breakdown of its functionality. Initially, the code extracts binary return values for the TSLA stock from the return column within a DataFrame labeled stocks. Next, it divides the binary return data into two sets: a training set binary train consisting of the initial 2000 values and a test set binary test containing the remaining values. A crucial aspect of the code is the establishment of a pattern length denoted as step, representing the size of the pattern sought within the data, which in this context consists of sequences of binary values. Through a series of 10 iterations, the code operates a loop to detect patterns in the test data akin to those identified in the training data. During each iteration, a sample window of length step is chosen from the test data. Alongside the subsequent value sample check, the code then scrutinizes the training data to pinpoint occurrences mirroring the identified patterns in the test data and retrieves the consecutive values following these patterns. By calculating the average value of the predicted next step based on the recognized patterns in the training data, the code evaluates the accuracy of the predictions against the actual test data. For each prediction, a comparison is conducted between the predicted value and the actual value from the test data to assess its correctness, appending 1 to a comprehensive record of total predictions for matches and 0 for mismatches. Upon concluding all iterations, the code concludes by determining the accuracy of the predictions through summation of the correctly predicted values, subsequently divided by the total number of predictions made. Ultimately, a display of the accuracy score regarding the model's predictions is presented. This code proves valuable for forecasting future values within binary time series data by leveraging historical patterns within the dataset. Examining this code snippet reveals its purpose in analyzing patterns within a time series dataset. Here's a breakdown of its functionality. 1. Initially, it establishes a starting point and window size to extract a sample from the dataset. 2. An empty list denoted as a is created. 3. A sample is extracted from the binary test data based on the designated starting point and window size. 4. The code then loops over a range of indices within the binary train data to compare segments of the data with the extracted sample. 5. When a perfect match is identified, accuracy score equals 1. 0. The starting index of the match is appended to list A. 6. Using Matplotlib, a graphical representation is generated to display the original time series data true in comparison to the segments of data from TSLA stock return values that align with the sample. 7. A reference horizontal line is included at E0 on the plot for clarity. This code snippet serves a valuable purpose in recognizing and displaying patterns or matches between the sampled sequence and sections within a larger dataset. The visualization aids in comprehending how the pattern recurs or manifests in the dataset. Such analysis proves advantageous in diverse domains like finance for spotting repeated stock price movements or in signal processing for identifying specific sequences within time series data. The provided code snippet serves the purpose of graphing stock data while emphasizing particular patterns for visual review. Here's how the code operates to start. It isolates a specific time frame from 2001 to 2011 from the TSLA stock dataset and locates the indices related to the return column within this interval. Moving on, it generates a plot featuring 3 primary lines. The first line showcases stock returns spanning from 2000 to 2020. The second line accentuates stock returns between 2001 and 2011 with distinct coloring and increased line thickness. The third line underscores stock returns within the 2010 to 2011 timeframe. Using the marker H and a unique color, it then loops through a Extracting a subset of data from the TSLA stock dataset for each element INA, comprising data for 10 consecutive days commencing from I. Subsequently, it visualizes these subsets employing specific colors and markers. Moreover, the plot incorporates a legend entry found patterns to aid in clearer visualization and comprehension of the highlighted patterns. Additionally, a horizontal dashed line is incorporated at the zero return level to provide a reference point. To wrap up, the plot is personalized with a legend, title, and labels, and then exhibited for review. This code holds significance in pinpointing and scrutinizing particular patterns within the TSLA stock dataset visually. By presenting the data with emphasized patterns, it facilitates users in deciphering trends and making well-informed decisions based on the discerned stock return patterns. This snippet simplifies a function call to meta-trading with stock TSLA, CLA 2018 as the argument, likely within a comprehensive stock trading project concerning Tesla's stocks with the ticker symbol TSLA and utilizing data from 2018. The MAD trading function likely incorporates a trading strategy involving the moving average convergence-divergence MAD indicator, a well-known tool in technical analysis for signaling buy and sell actions in financial markets. In this line, the output of MAD trading is assigned to two variables: profit and trades. Profit probably signifies the overall profitability of the trade tactic, while trades may hold detailed trade information throughout the trading time frame. Leveraging such code is crucial for automating trade approaches and scrutinizing past data to render well-grounded decisions. It empowers traders and analysts to test strategies on historical data, tweak parameters, and potentially unlock lucrative opportunities in the trading landscape. This excerpt appears to be a segment extracted from a probable Python programming project tailored for conducting financial analysis utilizing stock market information. Within this program, the function plotting MAD is implemented to produce a moving average convergence-divergence MAD chart representing the trading activities of Tesla stocks in the calendar year of 2018. The MAD serves as a prevalent momentum indicator employed for trend tracking, illustrating the correlation between two moving averages of a security's valuation. It encompasses components such as the MAD line, signal line, and histogram. Traders and analysts rely on MAD graphs to pinpoint potential trading signals by examining crossovers and discrepancies amidst the MAD line and the signal line. By honing in on the Tesla stock information from 2018, the code zeroes in on evaluating the price fluctuations and market tendencies of Tesla stocks specifically throughout that year. Employing the MAD indicator to visualize this dataset empowers traders and investors to render well-informed decisions grounded on the distinctive patterns unveiled within the chart. To sum up, the code constructs a MAD visualization of the Tesla stock data for the year 2018, delivering valuable insights into plausible trading indications and market trends. These observations can be pivotal for navigating investment choices within the stock exchange domain. This piece of code processes a roster of stocks and processes each one to ascertain returns applying the MAD moving average convergence-divergence trading approach for the fiscal year 2018. Initially, it generates an index of firms by browsing through the provided stocks. Then it sets up a vacant compilation termed returns. For every stock, the MAD trading function is invoked from a module called functions with designated arguments. Within the MAD trading function, profit and trading data are computed using the MAD tactic for the specified stock. The resulting profit is proportionately adjusted to reflect a percentage of the initial budget 5,000 through profit 105,000. The parental profit is rounded to 2 decimal spots and appended to the returns list. This script serves the purpose of evaluating stock performances employing the MAD trading tactic for the year 2018. It facilitates the comparison of returns yielded by individual stocks during that specific year. By automating the returns calculation process utilizing a defined trading approach for numerous stocks, it streamlines the analysis and decision-making process for investments. In this snippet of code, a pandas data frame is crafted by merging two distinct lists labeled companies and returns. The outcome is a structured data frame containing company and return columns. Subsequently, the data frame is arranged in a descending order based on the data within the return column. This particular piece of code serves the purpose of structuring and evaluating information associated with companies and their returns. By arranging the data frame, we gain a clear insight into the companies with the most robust returns and how they stack up against one another. What ensues is the facilitation of informed decision-making or the ability to create visual representations derived from the performance metrics of various companies. It is probable that this snippet of code invokes a function called btrading, likely stored from a Python script or module named functions. This function appears to be tailored for executing the Bollinger Band's trading strategy specific to a stock, like TSLA in this instance. Breaking down the code's functionality 1. The btrading function receives 3 arguments: a data frame comprising Tesla stock data from 2018 extracted from the stock's data frame or a similar dataset. 2 other parameters, U and L, presumably representing upper and lower bounds crucial for the Bollinger Band strategy. 2. The function likely outputs 2 elements: profit indicating the profit yielded by implementing the Bollinger Band's trading strategy on the provided stock information within the defined upper and lower limits. Trades, possibly a list or numeric value denoting the trades executed based on the Bollinger Band's approach. The Bollinger Band's trading technique hinges on utilizing statistical indicators named Bollinger Bands to ascertain whether a stock is overbought or oversold. The upper and lower bounds U and L are predetermined values aiding in decision-making regarding when to buy, sell or retain a stock considering its price fluctuations. Utilizing this code enables analyzing past stock data, specifically TSLA stock data from 2018, to evaluate the effectiveness of the Bollinger Band's trading strategy given the specified upper and lower thresholds. This analysis can be instrumental in making well-informed decisions concerning the trading of that particular stock. This excerpt forms an integral part of a financial evaluation procedure. It functions as follows. To start, it initiates an empty roster named returns. It proceeds to compute the earnings and trading frequency for each entry in the collection of stocks utilizing a designated trading mechanism known as btrading. The btrading operation receives distinctive inputs: the 2018 data specific to the entry in stock C, an allocation of $5,000, upper and lower thresholds of 0, 3, alongside instructions to suppress graph display and yield values throughout execution. The profit is gauged as a portion of the $5,000 allocation and is then rounded to 2 digits post the decimal point. Subsequently, the rounded profit percentage is attached to the returns collection. This code serves to yield profits grounded on a trading tactic executed on the stock details for the year 2018. This tactic involves the utilization of the Bollinger Band's trading system. The significance of this code lies in its role in evaluating the efficacy of diverse entities' stocks leveraging a specific trading methodology. By sequentially traversing the stock specifics and implementing the trading functionality, it computes the profit percentage and archives such data for subsequent assessment or cross-company contrasts. In Python, the following script leverages the pandas library to construct a data frame. By utilizing the provided lists companies and returns, the data frame comprises 2 distinct columns: company and return. Subsequently, the data frame undergoes sorting based on a return column in a descending manner, facilitated through the implementation of the sort values function. This methodology proves valuable for structuring and displaying data systematically. Sorting data serves a crucial role in enhancing analysis and comprehension, particularly essential when handling extensive datasets.